So today we're finishing up section 5.2, which is primarily on the mean value theorem, but it has some other things thrown in. And it's the other things that we're going to be looking at today. So trying to ignore the fact that it says that it's BC on the notes. I actually don't even use these notes with BC anymore. I do something completely different, but that's neither here nor there. So you probably haven't thought about this, but if you have two functions that are different, but they have exactly the same derivative, the only way that can happen is if they have a constant at the end that's different. You know, one has +7 and the other one has a -3 at the end. Everything else has got to be the same if the derivatives are the same. So if f prime of x is equal to g prime of x at each point of an interval I, then there is a constant c such that f of x equals g of x plus c for all x in that interval I. Now, it's possible that c is 0 and that f and g are actually the same function, but they can be different from one another. What this is leading up to, something I have hinted at multiple times, we're leading up to antiderivatives. So here, find the function f of x, whose derivative is cosine of x. So I know that the derivative is cosine of x. F prime of x is equal to cosine of x. And whose graph passes through the point 0, 3. All right, so then what's the simplest function whose derivative would be cosine of x? Sine of x, right? The derivative of sine is cosine. But here's the problem, is that if x is 0, f of x isn't 3, is it? But notice you can have this plus c. It can differ by a constant. So I'm going to say this is plus c. We'll talk more about it, but this is called the general antiderivative. Now, we want it to go through the point 0, 3. So we want 3 to be equal to sine of 0 plus a constant. Sine of 0 is 0. So that constant is 3. This is sometimes called, the 0, 3 is called an initial condition. You can think of it as a starting place. That's why it's called the initial condition. It doesn't have to be at x is 0. It can be anywhere. So once we know that c is 3, our function f of x is sine of x plus 3. So just in general, a function capital F of x is an antiderivative of f of x if capital F prime of x is equal to f of x for all x in the domain of f. And that process of finding an antiderivative is called antidifferentiation, which, although it's got a lot of letters, doesn't really score all that well at Scrabble because they're all, basic letters. No Q's, no X's, no Z's, that kind of thing. That and the only way to make it, pardon?
The only way you can play that word is someone start off with different.
Yeah, you could start with
and then went to anti.
exactly. Exactly. You'd have to build it by stages. You couldn't do it in one play because what do you have, 7 tiles when you're playing Scrabble?
You could do it in 2.
Yeah. You'd have to start with differ.
I mean, yeah, differ or different. I mean, it would have to be
Yeah,
like
different.
lines, and you just be like,
Yeah.
this one T, and then there you go.
Anyway, so let's find all possible functions with derivative f prime of x is equal to 1 over 2x to the 2/3 power. Then find the function that contains the point 8, -5. So that's our initial condition here. I'm going to rewrite the derivative. I really don't like it in that form. I would rewrite it as f prime of x is equal to 1/2 x to what power? Yeah, the -2/3 power. So now let's find the general antiderivative. So let's think about this just a second. How could we have ended up with -2/3 as the power? What did the power have to be before we took the derivative? 1/3, because we subtract 1 from the power. So this is going to have to be x to the 1/3 power. Now, when we take the derivative of that, we're not going to get 1/2, are we? We would get 1/3 x to the -2/3. All right, well, here's what we do. Think of it this way. When I take the derivative of the x to the 1/3, I'm going to have 1/3 x to the -2/3, right? To cancel out that 1/3 that's about to come here, I'm going to multiply by the reciprocal. So that when I take the derivative of the x to the 1/3, the 1/3 and the 3/1 will multiply each other out to be 1. And then this is plus c. So my general antiderivative is 3/2 x to the 1/3 plus c. The nice thing about doing antiderivatives, and I'll just be blunt, antiderivatives are harder than derivatives because there are some rules, but there's also, what could I do that would make this fit some rule that I know in reverse? It's just more difficult. Yes, sir.
So I thought we multiplied by 3 so that they would cancel out.
When I take the derivative, they will cancel out. So if I took the derivative of this, I'd have 3/2 times 1/3, and the 3's would cancel each other out. Slicker than pig snot.
We're not backwards.
So now I can use the initial condition to find the value of c that I want. So I want the function to be equal to -5 is equal to 3/2 of 8 to the 1/3 plus c. Now what's 8 to the 1/3 power? 2. And you're like, oh, thank goodness someone cooked this up so that it comes out nicely. So I get -5 is equal to 3 plus c. So c is equal to -8. So my function ends up being f of x is equal to 3/2 times x to the 1/3 minus 8. And you can always check these. That's one of the nice things about the derivative, is that you can check it, by an antiderivative, is that you can check it by taking the derivative. If you take the derivative of this, you're going to get 1/2 x to the -2/3, and the minus 8 is going to drop off because the derivative of a constant by itself is 0. All right, so that's one thing that's in this section. We'll go ahead and turn that over and we'll look at something else that's in this section. Increasing and decreasing functions. You guys talked about these last year, didn't you? In pre-cal? Whether a function is increasing or decreasing?
Like a lot.
Like a lot?
Like too much.
Yeah, they kind of, when they wrote the AP pre-cal curriculum, they're trying to get you ready to take calculus and actually nothing else, which is, I actually have a problem with that. Pre-cal is not just supposed to be get you ready for calculus. There are other important things in there that aren't in that curriculum, that should be, in my opinion, but
Seems like you really don't like AP Pre-Cal just in general.
I don't.
Just the test, the curriculum, everything.
Yeah.
Love it. Us neither.
It was like a harder algebra too. It didn't feel like. It didn't feel anything close to what we're doing in this class.
Gotcha. Well, some of it we'll come over. Like you guys did limits,
Yeah.
right? And here you did increasing and decreasing. This is the definition of increasing and decreasing. If f is a function that's defined on the closed interval from a to b, and x sub 1 and x sub 2 are any 2 points in that closed interval from a to b, then f increases on the, notice it's a closed interval, right? If, when x1 is less than x2, f of x sub 1 is less than f of x sub 2. And then the corresponding one for decreases. Okay, occasionally, and actually I've seen this in some curriculum that, saw it on Facebook where someone is doing a teachers pay teachers. Have you guys heard of that?
Yes.
Where, some teacher has written some worksheets or whatever and you can buy them from them. And they had this wrong. I'm like, nope. They said that it didn't include the endpoints. And I'm like, nope, that's categorically wrong. Someone pointed it out. Now, whether or not, the person who wrote it fixed it, I don't know. But it's like, yeah, you really should know your stuff a little better than that, especially if you're selling it.
I feel like the endpoints are like one of the more important parts of this.
Well, what they did was they said is that at that endpoint, it was neither increasing nor decreasing. And part of the problem with that is that we, generally speaking, we occasionally break this rule, so I have to say generally speaking, don't talk about whether a function is increasing or decreasing at a point. Because at a point, you just have a point. What we say is it's increasing or decreasing on an interval. You made a face, Sam.
I feel like we had maybe 50 questions last year saying, is it increasing at this point or not? It was just like
I'm gonna
beyond
say
graph.
there were probably 3 questions on the test about it.
Where they said, is it increasing or decreasing at this point?
Yeah, I remember a couple intervals.
Yeah, it's increasing or decreasing on an interval. The thing is if a point is inside of that interval, and the function is, say, increasing, it's increasing on that interval, then at any point, yes, it is increasing. It's just, you have to be really careful about it. Anyway, so one of the corollaries of the mean value theorem, and that's why it's in this section, is super important. We're going to use this a ton. It says if f is continuous on the closed interval from a to b and differentiable on the open interval from a to b, hey, that's exactly the same way the mean value theorem starts, isn't it? Those two things have to be true. Then, if f prime is greater than 0 at each point on the open interval from a to b, then f increases on the closed interval from a to b. And if f prime is less than 0 at each point in the open interval from a to b, then f decreases on the closed interval from a to b. You already kind of know this, right? We've talked about it before when we were doing related rates and all that kind of stuff. When we were doing related rates, I would ask you, is this rate positive or negative? And you would tell me it's negative. And I would say, why? It's because this quantity is decreasing. You already understand this at an intuitive level. But you haven't done problems with it. So let's take a look at this one. Where is the function f of x equals x cubed minus 4x increasing, and where is it decreasing? What we're going to do is take the derivative so that'll be 3x squared minus 4, and we want to know where is the derivative positive and where is the derivative negative, on what intervals. What?
No, just think to yourself.
Okay. So first what we want to do is find where could this change from positive to negative. Well, if something changes from positive to negative or negative to positive, it's got to be 0. It's also possible, and we'll talk more about it later, that you can have a place where the derivative is undefined and your derivative changes from positive to negative or negative to positive. Like if you have a function that looks like this, well, that function's not, the derivative is not defined at this point, but the function did change from increasing to decreasing and its derivative changed from positive to negative. So we're going to find where is this equal to 0. So that means that 3x squared has got to be equal to 4. So x squared is equal to 4/3, which means x is plus or minus. You have to remember to think about both of those. Too often students just think about the positive one. The square root of 4 is 2, and the square root of 3, well, there's not much I can really do with that. The question sometimes comes up at this point, do I have to rationalize the denominator? Depends. If it's a multiple choice question, they might rationalize the denominator, but they might not.
You didn't on the test.
Pardon?
You didn't on the test for the bonus.
Oh, on the, I haven't looked at the bonus.
Who's the square root?
Did they have a square root in the denominator?
All of that.
5 of the answer choices?
Okay. Yeah, and this is right off of an old AP exam, so. All right. So what I'm going to do to help, and we'll talk more about this later, this is an aid, it is not a justification. Sometimes on these problems they'll ask you to justify your answer. So negative 2 over the square root of 3 and at positive 2 over the square root of 3. Here f prime is 0 and here f prime is 0. Those are potential places where the derivative could change sign. Now, just because something is 0 at one point, does that mean it goes from negative to positive or positive to negative? Not necessarily. That's the whole, I don't know if you did this in pre-cal or in algebra 2, but when you had like a quadratic, I totally missed it. Let me try that again. A quadratic where it had, I'm going to miss it again, yeah, where it had a double root someplace, where it just touched it and then went back up. There's no sign change there, okay? So all I have to do, though, is test any point in each of these 3 intervals. So between negative 2 over the square root of 3 and 2 over the square root of 3, what could I check really easily? 0. If I substitute in 0 for x, what do I get for the derivative? -4. The fact that it's 4, nobody cares. All we care is that it's negative. So here, f prime is negative, which means that f is doing what? It's decreasing. When the derivative is negative, my function is decreasing. Now, I don't know what 2 over the square root of 3 is, but the square root of 3 is close to 2, right? So, okay, am I pretty safe in thinking, well, 2 is bigger than that, right? So substituting 2 into this, 2 squared is 4, times 3 is 12, minus 4 is 8. Here, f prime positive. So f is increasing. And then likewise, if I substituted in -2, I still get a positive 8 for the derivative. So here, f prime is also positive, so f is increasing. So f is increasing on open at -infinity, and then we go to -2 over the square root of 3, and it's closed at that endpoint. And closed at 2 over the square root of 3 to infinity. This problem doesn't ask you this, but if you were asked to justify that, that would be because f prime is greater than 0 on the open interval from -infinity to -2 over the square root of 3, and the open interval from 2 over the square root of 3 to infinity. That's how you would justify it if you were asked to justify it.
Will we be asked to justify it?
Certainly on the AP exam.
But like for these tests right now,
Sometimes I will, yeah.
this time will you?
Probably because you need the practice. And f is decreasing on the closed interval from -2 over the square root of 3 to +2 over the square root of 3. And again, your justification for that would be because f prime is less than 0 on the open interval from -2 over the square root of 3 to 2 over the square root of 3. Oops. And again, this is where, there's some arguments in textbooks and stuff. Someone might ask, well, what happens at 2 over the square root of 3? And you're like, okay, in calculus, we really don't ever talk about increasing or decreasing at a point if we can help it. You could say it's neither increasing nor decreasing, but it is included in the interval of where it's increasing and the interval of where it's decreasing, because it fits that rule that we the definition. I had a great argument with, well, it was a great argument because I was right and she was wrong, but at the AP reading one year, the lady who was sitting at my table was just vehement that nope, that shouldn't be closed. And I'm like, get a calculus book and read it. I mean, they all agree on this. This isn't, there are some things in calculus where some books say one thing and some books say another, and it really depends on how you define something. Every calculus book agrees on this. Anyway, and more importantly for you guys, this is the way the College Board says it should be.